This is a problem that I passed out for a class, and I'm doing it here in a video format, where we have an overhanging beam that is supported by a pin at A, and there's a strut BC, and we're asked to determine the reactions at supports A and B. In order to solve this problem, we would generally have to write two free body diagrams along with the equations of equilibrium. But there's a shortcut if we would like to use it, namely that strut BC is a two-force member. A two-force member is one that can be replaced by a single force that acts along the line that adjoins the two pins of the member. In class, I mentioned that we could prove to ourselves that this indeed was the truth by drawing a free body diagram of the two-force member and writing the equations of equilibrium, and that's what I've done here. Because this beam does not have any external forces that act in between these 2 points, we can define this force or replace it by a single magnitude that has a direction that's defined by this line where the geometry is given. But let's prove it to ourselves. If we take the moment about C here, we have a negative bx times the moment arm, 1.5, plus by times its moment arm, which is 2, and solving, we have a linear relationship between bx and by. Similarly, we can sum the forces in the x and in the y directions, where cx and bx are equal and opposite to each other, and the same thing with by and cy. So from these equations, we can see that we can define this magnitude of this force and show that it acts along this line if we then substitute this by into this expression. So once we've replaced this force, we can now draw our free body diagram of the overhanging beam, where we can write the moment about A, and in doing so, we have negative 900, which is this moment couple, minus 600 times 1, that's the moment from this force, plus force BC. Here's force BC, but the part that induces the moment is the vertical component of this force, so this is 1.5 over 2.5 times the moment arm, which is from here to here, so that's 2, which is why there's 2 here, minus 800 times the moment arm, which is 4. We can solve for force BC as following, and then write two other equations of equilibrium, the sum of the forces in the x and the sum of the forces in the y. The sum of the forces in the y, we get AY minus 600 minus 800 plus force BC times the vertical component, 1.5 over 2.5 is equal to 0. We can substitute in force BC and then solve for force AY. Writing the sum of the forces in the x direction, we have AX plus the x component of FBC, which is FBC, times the direction, which is 2 over 2.5, which is equal to 0. And from there, we can substitute in FBC, which is the magnitude, in here, and then solve for AX, so that AX is equal to 3.133 times 10 to the third newtons.